Très bien.
Bon. Tu l'as le micro? Oui, non. Il l'a. Ah. Thanks. C'est un petit test.
Tonight, we have the pleasure to listen to Jean-Pascal on Ypersele. So Jean-Pascal is a physicist, climatologist. He's a professor in the University of Louvain-la-Neuve in Belgium, and is vice president of IPCC, and a member of IPCC for a long time now. So he has a long story to tell us.
I am not a member. I'll explain why.
Oh, okay. So you are familiar with IPCC.
That's right.
Well, Jean-Pascal.
It means I have to explain a little bit what IPCC is, which I plan to do, and I'll explain who can be a member of IPCC, and I cannot be a member of IPCC. I'll tell you why, even if I'm vice chair of the IPCC. So I simplified my title a little bit. I'd like to speak about the subject I know best, climate change, and of course, linking that subject to the subject of the week, scenarios. Let's look a little bit at this beautiful picture of the planet taken a little more than 40 years ago on 17 December 1972 by the Apollo 17 crew. And let's look at another picture of that planet as it was 20,000 years ago, almost, without any clouds. Of course, it's a reconstruction, but it's quite rooted in the geological data. And you can see huge ice sheets covering North America, covering the northern part of Europe and Russia. Of course, Greenland, as today, that didn't change too much, but this is not just a few meters. This is 2 to 3 kilometers. 2 to 3 kilometers thick. There's so much ice there that the sea level, the global sea level, is 120 meters lower than today. 120 meters lower than today. The difference between this planet at the last glacial maximum, just 20,000 years ago, a very short period at the geological time scale, the difference in global temperature between this planet and this one, the one you know today, is just 4 or 5 degrees globally. I'm showing this because it gives, trying to give an impression of what it means to change the temperature on the global scale when one speaks about not the temperature in les Houches, but the temperature at the average temperature of the globe, to change that temperature by a few degrees. In the recent past, a few degrees meant melting those huge ice sheets, changing the sea level by more than 100 meters, and changing completely the habitability of the planet. You can see here this diagram showing the evolution of global temperature over those last 20,000 years ago. You can see what I just said. For the last 10,000 years, that temperature has been basically stable, plus or minus, let us round numbers like physicists like to do, plus or minus 1 degrees. We're not going to discuss about the whether it's 0.8 or 0.7 or 1.2, it doesn't matter. Plus or minus 1 degree, which is that long period during which civilizations and agriculture in particular developed. And before that, it was much colder, and it took almost, let's say, 3,000 years to gain those 4 to 5 degrees. I repeat, it took almost 3,000 years to gain those 4 to 5 degrees. Now, we're not talking, and these are the last numbers from the last IPCC report published at the end of September last year. We are now talking about gaining again, on top of the present temperature, 0.3 if we are in the very optimistic scenario with a lot of mitigation and extremely low emissions, even negative global emissions before the end of the century, as I'm going to show, up to approximately 5 degrees C globally. and still reaching and still rising after 2100. Now, Michel Lepetit asked me if I was going to give you some good news in my talk. I said this was not part of the mandate I received, so sorry. No, I got some indications about what I was expected to speak, but I didn't have that element. But still, without knowing that he would ask me, I will, at least for a short moment, give you some good news. The good news is that climate is not changing. I mean, look at this temperature. I mean, it's very well known. It's very well known. I mean, read so many newspapers, articles talking about the stable temperature over the last 15 years. I mean, where is climate change? I mean, why are we worrying about anything? I mean, actually, one has to look a little more at the context to see that this is a very cherry-picked view of the global temperature, just looking at those last 15 years, particularly 15 years ago. It means starting the comparison with the year 98, which was a very warm year. So, of course, if you start from a very warm year, it's hard for some time to have a clearly rising temperature. Actually, climate never stopped to be stable or even to cool. I mean, look at that cooling between this point and this point. Look at this cooling here. I mean, look at this big cooling here. This big cooling here as well. I mean, never stopped cooling, but well, that was the end of the good news. The good news part of my talk. This is a diagram showing averages decade by decade over the last 150 years. This is coming from the last IPCC report, showing that the last 3 decades have been successively warmer at the Earth's surface than any preceding decade since 1850. 1850 being more or less the period when enough data were available to compute a global temperature average. And it is even possible to say that for the northern hemisphere, for which the data span a longer record, this 30-year period was likely the warmest 30-year period, and you probably know that climate is usually defined over a 30-year period. So you could actually attack this diagram by claiming that a decade is not significant, and to a certain extent it's correct. 10 years is not enough to speak about climate. But even if you take the last 30-year period, well, that last 30-year period is the warmest of the last 1400 years. So we are really seeing some significant change. Now, I promised to explain a little bit what the IPCC is and maybe why I'm not a member, but that's not essential. It was created a little more than 25 years ago by the World Meteorological Organization and the United Nations Environment Programme, 2 UN agencies, because the mass of the scientific literature available on climate was becoming unmanageable for individual scientists, but also for policymakers. And they wanted to have an objective source of information, a rigorous source of information about the body of the scientific literature, not just from one article or from one source, but the body of the scientific literature, assessed in a rigorous way, which I will briefly explain, and to cover with that assessment process all the dimensions of the climate change issue. I mean, the science of climate change, the physics of the climate system, I mean, whether climate is changing, what are the factors, natural, humans, influencing climate, what are the what is the possible evolution of the climate system in the future based on scenarios, there we are, but also to look at possible impacts of climate change, both on ecosystems and on human systems. And then, so that the IPCC doesn't only produce bad news, also there's a group in IPCC working on the solutions, both in the adaptation side and in the mitigation sides. I think I told you this, the IPCC website where all the reports are published is this one. A very key characteristic of the IPCC reports, and it's something to remember when we will discuss scenarios, is that the IPCC has to be policy neutral or policy relevant without being policy prescriptive. In other words, contrary to what is repeated many times, the IPCC doesn't recommend and never recommended that we stay below 2 degrees. It's not the IPCC who decided that or who gave that piece of information. It was at some point a political decision not to, to try to stabilize the climate so that it doesn't warm more than 2 degrees. That decision was presumably informed by the IPCC reports, and that the description of the impacts and the increasing severity of those impacts with increasing temperature, but never the IPCC made that choice between +1, +1.5, +2, or +4 degrees. That's a political choice which was made first in Europe in '96 and then in Copenhagen in 2009 at the global level. So we have to walk on the fine line between being policy relevant, sufficiently interesting for policymakers and decision makers, but without entering their territory, their turf, because they've been elected to take decisions, and I think that's exactly what Yves said on the first day. Yves Bréchet said on the first day that there's a difference between what the experts can do and what the policymakers have to do. So the IPCC is divided mostly in 3 working groups. One on the physical science basis, that's the one which completed its report at the end of September. Working Group 2 on impacts, adaptation and vulnerability is going to finalize its report at the end of March this year. And Working Group 3 will publish its report on mitigation, that's basically emission reductions, at the middle of April. There's also a task force dealing with methodology for inventories. A few words, because I think this is not known enough, about how the IPCC works. The members of IPCC, and this gives me the opportunity to say who are the members of IPCC. The members of IPCC and the only members of IPCC are governments. The 195 governments of the world are the member of IPCC. Nobody else is a member of IPCC. You can be a member of the Bureau of IPCC, that's something else. I'm a member of the Bureau of IPCC. Those who know Jean Jouzel, French member of the Bureau, is a member of the Bureau, but France is a member of IPCC, no individual. And the group of members of IPCC meets from time to time in a what's called a plenary setting. They don't meet very often, usually once a year. Now this year they'll meet 3 times, but usually it's once a year. And they meet at the beginning of an assessment cycle to decide what the table of content of the next report will be. That's a very important moment because it's a time when policymakers say what they are interested in, and it changes with time. We are now at the 5th assessment report, and the table of content, of course, contains elements which were present in the first table of content 25 years ago, but also there are new elements. For example, the policymakers insisted for this report that we talk more about the problem of acidification of the oceans, which is also related to CO2 emissions. They also insisted that we talk more about geoengineering and assess the literature on that technique or group of techniques, etc. So, but once the table of content is finalized, and this comes at the end of a long dialogue between policymakers and the scientific community, which take between one year and a year and a half, so it's serious work with a number of workshops, etc. Excuse me. The Bureau, I knew I had to take this. The Bureau, with a group of 30 scientists elected by the plenary, excuse me, then select the authors. To give you an idea, at the beginning of this assessment cycle, we received 3,000 curriculum vitae in the beginning of 2010. We selected 831 authors to write the report, the 3 volumes, the dozens of chapters in those volumes. I mean, it's 14 chapters in volume 1, 30 chapters in volume 2, and something like 12 in volume 3. I'm not sure for volume 3. And then the scientists start their work and they assess the literature, they produce a draft, and that draft is relatively quickly submitted to a first round of review. And after collecting the comments from that round of review, first review from experts, the authors have to start again to rewrite their text, taking into account each of the comments. And it means taking into account thousands of comments, actually. The last volume, volume 1 of the 5th report, the one which was finalized in September, received more than 54,000 comments over the 3 cycles of review that took place over the 3-year period for the writing of the report. Now, it's not only the authors and the experts' comments, they are not left alone. Each chapter has between 2 and 3 senior scientists called review editors who are there to, in a friendly way, but in a firm way, when needed, accompany the authors to make sure that they take into account each comment, whether it comes from the government of Saudi Arabia or from Greenpeace or from the government of France or the US or the US, that each of those comments is taken on board in an objective way. And the authors have to indicate in a huge Excel sheet next to each comment what they are doing with it. And the review editors, those senior scientists accompanying the process, are checking that it's fine to do what the authors said they would do. So it's a very rigorous process. So I'm explaining that because, you know, some people write things about the IPCC without having any idea of what the IPCC is doing. And for example, they write that at the end of the process, at the other plenary, which is at the end of the process, you have a number of diplomats voting, representing their country and voting on the science of the report. And that's completely wrong. It's not at all what happens. What happens is that representatives of governments tell the scientists who prepared the summary for policymakers, which summarizes, and this is the summary for policymakers of the last report. It's a 20-page summary of the 1,500-page volume 1 that was published Friday last week in its nicely laid out form. And then in that interaction between the authors and the government's representatives tell the authors, here you are using jargon. Here you're talking about petagrams of carbon. Please, my minister is not going to know what a petagram of carbon is. He's used to talk in tons of CO2. Please write your thing in tons of CO2. Or there you are very affirmative, but on page 372 in the report, you are much more cautious. Don't you think that you should lift some of the context or the caution that is in the chapter to the level of the summary for policymakers? Okay, and there's a dialogue between the scientists and the government representative. But what's key is that the scientists, the authors of the report, have the last word. So the science is not changed by that process. It's only clarified, and the text is clearer. I mean, I'm not claiming it's as readable as a novel, but at least it's at least it's very rigorous and clear and unambiguous. Let's say. Okay, so the IPCC, with that long process, produced a number of reports. The key reports are the assessment report. 4 assessment reports have been published completely, and then the 5th one is in the process of being published. Each of them has had a number of effects on the international negotiations, and the 5th assessment report will be very important in the run-up to the Paris Agreement, hopefully, and also a process which is happening now, and which is the review of the 2-degree objective. Some countries, actually many countries, wishing to have that objective changed to 1.5 degrees, which would mean, if it was decided, that emission reductions would need to be even stronger than what would be needed for 2 degrees. So I told you about the schedule already. It's summarized here. I mean, there's the last element that's in October. There's a synthesis report that will come out. I'd like to tell you a few things about what's in the Working Group 1 reports, because that will serve as an introduction to what I would like to tell you about scenarios. So the Working Group 1 report has 14 chapters, but also for the first time an atlas of regional projections, which allow policymakers. That was also a request from the plenary at the beginning of the process, that the report needed to be as localized as possible, to provide information as relevant as possible to people where they are, and not only a global picture. You have some numbers there that you can read by yourself, and the 3 main messages from the reports are here. The first one is that warming of the climate system is unequivocal. You could say, well, this was said in 2007 with exactly the same words, and you would be right, but it's significant that exactly the same word I used now, after all the artificial discussion in the media around that so-called hiatus, which I tried to show on my fake temperature curve, I mean not fake, but cherry-picked temperature curve. So the fact that the IPCC, after its very rigorous and detailed assessment, comes with exactly the same conclusion as before is actually quite significant. Human influence on the climate system is clear. It's another clear quote from the last report, and I'll say a few words to illustrate. I show you a diagram or two to illustrate that, and then the last point, which is of course very important in the context of the climate negotiations, is that limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. And this diagram, which you see here, which you will see better a little later, which actually links on the x-axis, the horizontal axis, the accumulated CO2 emissions over time since the pre-industrial period, and the global temperature increase, and shows that the relationship is approximately linear, is actually a key new diagram of this report, and I will also try to relate that and some of the details of that diagram to the scenarios which I'd like to discuss as well. So on the first point, the warming is unequivocal. Well, this is the diagram showing that except where there are, and it's especially for them, a few climate skeptics here in this part of the US, climate is actually warming almost everywhere. Where it's white, it's only where data were not available. not enough data were available to talk about the trend over that almost a little more than 100-year period. You also see that the oceans are warming less than the continents. There's another slightly cooler place or place where there was some cooling south of Greenland, but that's just for a reason of ocean circulation.
Can I ask
Sure.
about these white surfaces? How is it taking into account the calculation the average temperature? Is it leaving out, or is there some kind of interpolation?
Well, the average, when a global temperature is given, it's a weighted temperature on the sphere. And I believe that those regions are just taken out because, here you could argue that you could interpolate, but here, even if, of course, on a sphere, the area here is not as large as maybe what appears here, but in total, the two polar regions there, it would be a little bit difficult to interpolate there. So I think it's just left out of the...
The warming is larger at high latitude.
Yes.
Then maybe
but
real temperature change is larger than what is...
That's right, but what is shown here is the trend, square by square, over the period in degrees, in degrees over that 110-year period. So I don't think anything is biased there, because this is not, this is a global picture, but what it shows is the trend for each point, actually. Now, another very clear indication that human activities are really changing things on a large scale is when you look at these CO2 concentrations, and these are measurements or reconstructions, at least until then. And when you see that over the last 800,000 years, almost the last million years, the concentrations, and of course most of this comes from the analysis of ice cores in Antarctica or Greenland, and the composition of the air trapped in small bubbles in the ice. Most of that time, the concentration, which is measured in ppm, parts per million, oscillated between, let's say, 200 and 300. And as you probably heard, last May, we hit for the first time in probably a few million years, the value of 400 ppm. We're now slightly below. Right now, we are 396, 397. It fluctuates on a daily basis. You can go and look at the measurement in Mauna Loa, that place on a dead volcano in Hawaii, where measurements are made every day in a very rigorous way. But soon, again in May, we'll probably go a little above 400 ppm, because of course there's a seasonal cycle, and we're just right now again on the climbing curve to the next local maximum. And you can see that the projections, according to different scenarios, well, there you see the word scenario for the first time. A lower scenario for the end of the century gives you something like 550 ppm, and the high scenario gives you something like 900, 3 times the concentration, the maximum concentration over most of this period. So we are clearly changing the composition of the atmosphere as far as CO2, which is a powerful greenhouse gas, which traps infrared radiation close to the surface and heats the planet. And so this, of course, fuels the question, is the warming in climate, which I just showed before, caused by this increase in CO2, or is it due to natural factors? And of course, it's one of the key questions the IPCC is asked. Because if it was only coming from natural factors, that warming, there wouldn't be much to do. We would just have to try to adapt as well as we can. But the analysis, the attempts by climate models to reproduce, for example, this is just one illustration. There are, of course, many other studies attempting to reproduce other characteristics, but this is an easy one to explain. to reproduce that observed global temperature curve, which you have seen already, with models in two different settings. One setting represent the results of which are represented by the blue line. This is the average, the blue line, the thick blue line being the average of a number of thinner blue lines coming from models in the same setting. And that setting is that those climate models were fed, if you like, only by natural factors. So volcanic eruptions and the small changes in solar activity. And that's about it. I mean, there's no, on this time scale, there are no other significant natural factors. And the red curve is coming from simulations which are forced, again, by those natural factors, which of course continue to be important, plus the human factors, the greenhouse gases, and the classical air pollution, smog, etc., which actually has some cooling effect on climates. And as you can see, at the times of the first assessment report in 1990, well, there was a difference, and the red curve was a little closer to the observation. But if you take into account the uncertainty around the average, it was not clear yet that it was the simulations with the human factors which were clearly representing better the observations. So at that time, the IPCC wrote the unequivocal detection of what needs to be understood is of the human influence is not likely for a decade. Actually, it only took 5 years to go a step further. Let me go a step further here. The balance of evidence suggests a discernible human influence, and the present tense is used here. So it means it's becoming visible at this time, the IPCC wrote, that human influence is playing a significant role. And then with time, it became clearer and clearer. Most of the warming of the last 50 years is likely, the IPCC jargon is a probability of 67%, due to human activities. Then it became very likely, which means for us 90%. And the last report says extremely likely, because with time, the difference between those blue simulations and those red simulations only diverge more and more. So this is one, it's not the only, but this is one of the key elements on which serious climate scientists rely, because not all are, rely to conclude that human activities have become now the dominant factor at this time scale. I mean, we're talking about since the middle of the 20th century. We're not talking in general. Since the middle of the 20th century. And that's quite important because it means then that one can do something. I mean, that's the good news, you could say, because it means you can do something about it. If it was only a natural phenomenon, you would just have to adapt. If it's mostly human, the good news, the good part of that news, at least, is that there's something to do about it. Now, the last diagram in that report, which is pretty important, and again, those things are related to 4 scenarios I'd like to discuss a little more, a little later, I'll explain. This diagram I showed in a small format shows the relationship up to now between the total anthropogenic, means of human origin, CO2, since 1870, which is not the beginning of the Industrial Revolution, but it's the beginning of serious data about fossil fuel emissions and climate. And the relationship between that and the temperature anomaly above 0 being 1870 also, let's say. I mean, the 20-year period centered on that. And you see it's more or less linear. But then, and behind this, there are thousands and thousands of supercomputer and simulations for for those four, and I'll explain in details what they are, scenarios, the new representative concentration pathways, which are one of the categories of the scenarios that were used in the last report. And you of course, the details, and of course, I mean, I know that's coming. There is some uncertainty about around this. It's not a straight line, but overall, it's basically almost linear relationship between cumulative emissions and temperature, which is pretty important. I mean, it's the first time that things were presented this way, because it means that if we really want to stay under that 2-degree limit, which up to now is the internationally agreed limit on the warming, then you can, and assuming only CO2 is playing a role, then you can just do this, and more or less, and you get here, which is a round number, which is nice, 1,000 gigaton of carbon, and you can multiply by 3.7 to get that in gigatons of CO2. And it doesn't depend so much on the scenario. I mean, you can see the different colors, and we'll see later what they mean exactly. What they mean mostly is that, particularly for those three colors, is that you go much further than 2 degrees. And if you are on the highest scenario, which is the red one, you go faster there than with the others. But apart from that, the basic relationship is quite clear, and it means that for the first time there is a presentation of the issue in a way that every additional ton of CO2 gets us closer to that 1,000 gigaton limit. Now, of course, there are other gases than CO2, and if you take into account the other gases, it's actually not 1,000, it's 800. And then if you also look at what could be released by permafrost melting, which is not very well known, but which is between 50 and 250 gigaton over the course of the 21st century, at least for the highest scenario. And if you also take into account that until 2011, 550 gigatons of carbon have been emitted already, the margin of maneuver is actually quite small. Let's speak more now about scenarios, because that's why you came here, why we all came here, isn't it? Well, the definition of a scenario in the IPCC glossary, which also was subject to negotiations, review, etc., so it has some value. I'm not saying this is the best definition you can find, but it's interesting to know that the definition of scenarios used by IPCC is this one. And I highlighted a few important words. A plausible description of how the future may develop, not will develop, based on a coherent and internally consistent set of assumptions about key driving forces and relationships. Nothing to surprise you, I'm sure, but what's important is, and of course, you understand now maybe a little better the remarks I made 2 times this morning. Scenarios are neither predictions nor forecasts, but they are useful to provide a view of the implications of developments or actions. There are many kinds of scenarios in IPCC. You have socioeconomic scenarios touching those variables that can be transformed into emission scenarios of greenhouse gases, and then you have, of course, different behavior for the different gases, but also other substances like aerosols, dust, other chemically active substance like SO2, for example. You also need scenarios for changes in the surface characteristics, and land use and changes in land use cover are also important part of the scenarios if you want to force climate models in a coherent coherent way. Those emissions, at least those dealing with carbon, enter a carbon cycle model. The other substances may enter another kind of chemical model, sometimes with many reactions, allowing the models to compute concentrations. And there's a big difference between, of course, the emissions and the concentrations. The emissions is a flow, a quantity per unit time. A concentration is an amount present at a given moment in time in the atmosphere. So it's quite different. And you need a model to relate one and the other. And one important characteristic of CO2 is that the residence times of CO2 is quite long. I mean, it seems that 20 to 40% of the CO2 emitted today will stay in the atmosphere for more than 1,000 years, which is more than what we thought before. And approximately 1/2 of what we emit, 1/2 of human emissions remain in the atmosphere today, while the other half is absorbed by forest, vegetation, soils, and oceans, about half and 50-50 approximately. At least those are the present numbers. That enters, those numbers, those concentrations then enter climate models, computing atmosphere, ocean dynamics, cryosphere, taking into account radiative transfer, clouds behavior to the extent it's possible to represent them, because that's a weak point in climate models. And then you can produce climate projections. And with those, on the basis of those climate projections, you can, in a further step, use a selection of those projections, and you can label them climate scenarios then, another kind of scenarios, characterized by a few important variables, and then look at what that means in terms of impact, vulnerability, and risks to people, economic activities, ecosystems, etc. So there's a whole information chain in the process. Now, for a long time, the IPCC and still some work published now in 2014 is still based on this special report, an IPCC special report on emission scenarios. That's where the acronym SRES comes. And a key element, a key characteristic of that report was, and this is the cover of that report published in 2000, was, and this was for political reasons at that particular time when the Kyoto Protocol was had not entered into force already. The US had decided not to ratify it, etc. So there was a mandate given by those members of IPCC to the scientists designing the scenarios on behalf of IPCC not to consider in that family of scenario any climate policy, forbidden. So they could design all the scenarios they wanted, but they couldn't have in that 1,000-page volume, which is that special report on emission scenarios, anything labeled climate policy, which is pretty important. And the third assessment report and the fourth assessment report, third assessment report published in 2001, fourth assessment report published in 2007, and still part of this report are based on those scenarios, which are based on a tree of driving forces. I mean, you can probably hard to read: population, economy, technology, etc. And they were broadly organized around two axes. One was the vertical axis separating the A scenarios and the B scenarios, where you had economic, more attention to the economy with the A scenarios, more attention to the environment with the B scenarios. And then there was a horizontal axis where the number 2 there related to scenarios where things were happening more regionally, more locally, with less trade and less exchanges in the world, while on the other hand, on the left part here, with the number 1 here, the economy was much more globalized. So there was a family of scenarios built on those drivers. And this spaghetti plate here of scenarios are the S-RES scenarios. Okay, these are, for these S-RES scenarios, just the emissions of CO2 equivalent. So it means that the effect of all greenhouse gases were summarized in an equivalent quantity of CO2 in gigatons CO2 equivalent per year. So these are emissions. And you have the value here over the 21st century. So you had big differences. I mean, this is about 30 gigatons, and this is more than 120 gigaton at the end of the century. And you see here the translation in terms of warming in degrees C above the temperature in 2000 for those 6 scenarios. Don't look at these numbers because this is confusing, because this has nothing to do with those scenarios. I mean, that's okay. What's interesting is this. So this corresponds to this emission scenario, the scenario B1. And this one corresponds to the A1FI scenario, which is the light blue scenario there. Now, for each scenario, you see an uncertainty range. You see this point here, which is thicker, which shows the central value, but there is an uncertainty range for that particular scenario, which is shown here, and the same here. So when and these are the numbers for AR4, the previous report. So when speaking about uncertainty, when it is mentioned that the IPCC projects that by the end of the 21st century, or projected, because these are the numbers from the previous report, okay, projected that the temperature would increase between 1.1 and 6.4 degrees C by the end of the century, this is where those two numbers come from. It's the extreme values. 1.1 is for this lowest scenario for the model, which is the least sensitive. And the 6.4 value comes from this high scenario, the A1FI, FI standing for fossil fuel intensive, and the most sensitive model. So it's not because the IPCC and the climatologists don't know anything about the way climate works, and the uncertainty is not as large as that. I mean, 1 to 6 is a big factor. No, it's because this range from here to there combines the human uncertainty on which scenario will be the correct one in the 21st century. And that's a scenario that's an uncertainty which is irreducible. I mean, nobody can predict what will happen because it depends on the decisions that are not taken yet. Of course, we can have ideas, we can guess, we can do many things, but we cannot predict for sure what will happen. And the other source of uncertainty is for each model, for each scenario, the uncertainty coming from the scientific uncertainty that remains today about the climate sensitivity for a change in the forcing factors. Now, there were other scenarios used as well in the past, and they played a very important role in a policy context. And those were the scenarios leading to stabilization at different values. So here, what is shown here in this vertical axis is the equilibrium global mean temperature increase. So it means if in function of the concentration in terms of CO2 equivalent, and these are ppm again. So it means here, for example, that for 500 ppm CO2 equivalent, if you wait long enough for climate to stabilize at that new concentration, if you take the average model, because again there is uncertainty, these are the most sensitive model, the least sensitive model. If you take an average model, 500 gives you a little less than 3 degrees, etc. So you can relate, for example, the 2 degree target on this value on this diagram to the concentration, which is well known, the 450 ppm CO2 equivalent. Just remember that this is for the average model. And we don't know what the sensitivity is. I mean, it's probably 3 degrees for a doubling in the CO2 concentration. Now, if the real sensitivity was this one, actually the concentration threshold would be much lower. And inversely, if the real sensitivity was this one, which we would be much more comfortable because we could wait until 525 or 530 ppm to be above 2 degrees. And it is possible by either doing inverse modeling or making many simulations and trying to get those numbers to relate those concentrations to emission trajectories over the 21st century. And you see there already that to be in this zone here, which is in the last report, the 2007 report, the first zone for which there were sufficient, a large enough number of simulations to provide solid numbers, to be in that zone, which actually is most of the time slightly above 2 degrees, as you can see. I mean, if you take an average model, this is above 2 degrees, it's from 2 to 2.4 degrees. To be in that zone in terms of concentration, in terms of emissions, you have to be somewhere here. And the bad news already in 2007 that very few people have realized actually was that the horizontal axis, the zero line, is not here, it's here. Probably many people didn't want to look where the zero line was, because what it means is that even in 2007, it was quite clear that to stay under 2 degrees, you had to get to zero emissions, zero global emissions, way before the end of the 21st century, which is not at all the message that came from this table, which was published also at the same time, showing that to be between 2 and 2.4 degrees, you needed to reduce emissions in 2050 compared to 2000 by 50 to the 85%. Actually, those numbers, which are repeated so often and have been repeated yesterday and today, they come from this diagram. If you digitize this diagram, you will see that this is 85% reduced compared to 2000, and this point is 50%. But this is a very cherry-picked view of this diagram. It is just what is happening in 2050. It doesn't tell you anything about the much bigger challenge, actually, to continue the reductions and to go to even negative global emissions well before the end of the century. And this is not in the last report. This is in the report published in 2007 already. Okay, so this is not new information. Now, just as an aside, I mean, a small remark in passing about the comparison between the emissions, the real emissions, and the scenarios, the most recent scenarios. You see that, and this has been said already, we are closer to the upper part of that family. Now, of course, the IPCC couldn't stay with that old family of scenarios published in 2000. Many things had happened in the world since, but also everybody accepted, there were also some political changes here and there, accepted that what was needed, particularly after Copenhagen, was to have officially stabilization scenarios. And stabilization scenarios leading to the possibility of staying either under 2 degrees or even under 1.5, given that in Copenhagen a 1.5 target had been quoted already. So actually, even slightly before Copenhagen, the IPCC decided that it was high time to prepare a new family of scenarios and to gain time, because in 2007 it was almost too late. We knew then that it would be too late to be ready with new scenarios for the AR5, this assessment cycle. So we decided to take a shortcut, and this is what led to the RCP. We decided to decouple the emission scenario developments and the climate modeling needs, which actually, with all due respect to economists and engineers and scenario developers, etc., the climate modelers, they don't need to know where the emissions are coming from. Climate models, they don't care whether the CO2 is coming from a car, a coal power plant, or any other source. It just wants to have global numbers, and for the aerosols, regional numbers, but for the greenhouse gases, most of the time, what is needed is only the global numbers. So there were, I will try to accelerate a little bit, but I think I told you the main things already. There were quite a number of meetings to organize the so-called parallel approach, which decoupled the design of the so-called, let me show you that, because that will be easier to understand. The representative concentration pathways, which is what the climate modelers needed to start the new climate simulations in order to be in time with the end of AR5 in September 2013. And these are the scenarios that were designed. Where do they come from, and what are the units in which they are expressed? They are a bit strange in the context of what has been discussed here up to now. They are expressed in watts per square meter. Okay, so because that's what the climate models needs mostly. What is the additional heating flux at the top of the troposphere, between the troposphere and the stratosphere, coming from the increasing concentration in greenhouse gases, etc. And again, climate models, they don't care where the greenhouse gas come from. They want those numbers and the evolution of those numbers. Now, how were those scenarios selected? Well, using a number of criteria. Remember, we wanted to shortcut the process. We wanted to have quickly a new set of scenarios that we could give the climate modelers so they could immediately start their supercomputers and do the computations, which takes months and months and months in order to be ready for the September 2013 deadline. It had to be compatible. So what we did was use published scenarios which were available in 2007. Not design new scenarios, but take existing scenarios and find a number, an even number, not an odd number, not 3. If you take 3 scenarios, then the tendency is to take the middle one. For policymakers, they don't want to. So we make their work a little more difficult by deciding explicitly that we would have a family of 4 scenarios. Then they cannot take the middle one. It's much more difficult. So an even number of scenarios selected in the full range of scenarios in the literature. From the highest scenario, the most terrible business as usual scenario you can imagine, burning as fast as you can, all the fossil fuel you can find, etc., with growing population, whatever. But also the lowest scenario built by the most volunteer experts wanting to protect climate and find all the ways to decrease emissions. The data had to be available for all the forcing agents and also for land use. That was, of course, important for the modeling work. And the scenarios had to be sufficiently separated from each other to allow the results of the simulation to be distinguishable. So the highest one was the most terrible scenario. This was the lowest scenario one could find in the literature in 2007. And those two were the scenarios that were more or less in between the two extremes at more or less equal distance. They were also published by different institutes. You probably recognize some of the models there, because those scenarios were coming from most of the time from integrated assessment models, which had a very elaborated methodology to get the numbers. But the climate modelers, they'd only care about those curves. Okay, so this was done. It was also decided to extend them in a simplified way until 2500, because to study sea level and the effect on ice sheet, it's very important to be able to do long simulations. Of course, if you ask an economist to say something about the economy in the 23rd century, he will think that you are crazy to ask that question. So, but for climate models, it's very important to be able to have in watts per square meter. So this is not GDP or tons of equivalent oil or whatever. It's very important to have long-term scenarios as well. These are all the institutes which participated in that scenario design. If you just Google IASA and RCP, you will get all the data. Then it was also later, and this was the beauty, quote unquote, of the parallel process. Later, there was another process which is a bit messy, and I'm not the best person to talk about it. I don't know if Patrick Criqui is still here. He left. He would have been able to say more about this. But there was another process to try to, after the fact, build new socioeconomic pathways that would be coherent with those representative concentration pathways that the climate modelers needed. But those people had a little more time to do that. And this is the division of the 5 categories of SSP for the socioeconomic aspects, starting from the challenges to adaptation and the challenge to mitigation as the two dividing axes. It's getting even more complicated, and I'm even less able to comment this in a clever way. There were also shared climate policy assumptions, SPA, to supplement the SSPs, and then you could combine the SSP and the SPA to link to RCP, but I think it's too late to look at those details. I think I said enough what the RCPs are. You'll be able to read that on your own. These are now the results with those RCPs in terms of simulation, at least for the two extreme. The top one, the bottom one, with the uncertainty again for the four scenarios, you have the number. You see now that for this scenario, the bottom number is 0.3. For this scenario, the upper number is 4.8. And of course, at first guess, 0.3 is 4 times lower than 1.1 from the previous report. Remember that the scenarios behind these simulations have nothing to do with the scenarios before, because the SRES scenarios had no climate policy. This is a very extreme scenario, actually. The results in terms of temperature at the end of the century are quite different. As the co-chair of Working Group 1 says, we have the choice between those two kinds of words. They have also quite a number of differences for other parameters, for example, sea level. You see the range for the lowest scenario is of the order of 30 centimeters for the bottom value, up to 1 meter. The other extreme for the upper value. It also makes a big difference in terms of the acidification. You probably know that if you add CO2 to water, it acidifies. That decrease in the pH of the global ocean has been observed already. That's what's shown here. And this is the